want to find an algebraic rule for differentiating a function that has the form u over v, the form of a quotient, where u and v are both functions of x. And we could develop this algebraic rule by simply stating the definition of the derivative, the limit as delta x approaches 0 of this difference quotient, the change in the value of u over v divided by the change in x. And there would be a lot of algebra involved, but instead of doing it this way, I'm going to suggest another approach. What if we think of u over v as being a product, u times 1 over v? We already have a product rule, so we'll use the product rule. It's just the second factor times the derivative of the first plus the first factor times the derivative of the second. The only unknown territory we're entering into is this second factor of the second term, the derivative of 1 over v. So you really could address this problem by developing a rule for taking the derivative of the reciprocal, the derivative of 1 over v with respect to x. And I think it's a good idea to make up a reciprocal rule and then use that to develop a quotient rule. So I'm going to cross all of this off and we'll start over again. What if we wanted to find the derivative of something that has the form 1 over v? We're going to invent a reciprocal rule. So I will write the definition of the derivative, and it's a difference quotient. In the numerator we have the difference of the reciprocal. This is the reciprocal at x plus delta x, and this is the reciprocal at x, and we divide it by delta x. In order to evaluate this limit, I'm going to clear the fractions in the numerator by multiplying the top and bottom by v times v plus delta v. And when I distribute those two factors over the two terms in the numerator, the denominators will cancel, and this term will simplify to v, and this term will simplify to v plus delta v, and when I subtract, I'm left with negative delta v, and it becomes the limit as delta x approaches 0 of negative delta v over delta x times this leftover v times v plus delta v on the bottom. This limit can be evaluated because we have a factor in there whose limit we know. The limit of delta v over delta x is the derivative dv over dx. And the other part of the denominator, when I set delta x to 0, then delta v vanishes and it becomes v squared. So the limit is seen to be negative dv over dx divided by v squared. And there it is. We now have the reciprocal rule that we were seeking. So let me state this officially. The reciprocal rule says that when you take the derivative of something that has the form 1 over v, you get negative the derivative of the denominator divided by the denominator squared. And let's check this. Let's try using it. What if we wanted to take the derivative of 1 over x squared? Really, we know 1 over x squared is x to the negative 2, so we could just use the power rule. But let's try our new reciprocal rule tool on it and see if that works. So we take negative the derivative of x squared in the numerator. That was this part, negative dv over dx. And we divide by v squared in the denominator, and we get x to the fourth in the denominator. When you simplify that, it becomes negative 2x to the negative 3, which we knew was the correct answer from the power rule. So now we've confirmed that the reciprocal rule worked in this case. Or an even better demonstration is we do something silly like the derivative of 1 over x to the negative 3. We're really taking the derivative of x cubed here. Let's see if we get 3x squared. So we have negative the derivative of the denominator divided by the denominator squared, and when I simplify that I get 3x squared, so it works. So now that I have established the reciprocal rule, let me back up and go to the point where I needed a reciprocal rule. That was right over here. Now I've been working on trying to develop the quotient rule, and I found I needed a reciprocal rule, and now I have one. So I can continue with this work. The derivative of u over v then is seen to be, we'll take this first term and rewrite it as du over dx divided by v, and then the second term is from the reciprocal rule, so I have u times negative dv over dx divided by v squared. I just applied the reciprocal rule. And then if I take these two fractions and I put them over the common denominator of v squared, I get the standard form for the quotient rule. The quotient rule is the derivative of u over v is v times du over dx minus u times dv over dx divided by v squared. Let's put it up on its own page now. The quotient rule says you take the denominator multiplied by the derivative of the numerator, you subtract the numerator times the derivative of the denominator, and the whole thing gets divided by the denominator squared. That's the form for the quotient rule. And to memorize it, I want you to notice that it's a little bit similar to the product rule, so let's compare them. The product rule says the derivative of uv is v du dx plus u dv dx. The quotient rule says the derivative of u over v is v du dx minus u dv dx over v squared. Notice that if you took the product rule and you replace that plus with a minus, you get the numerator of the quotient rule. This is the product rule in differential notation, the quotient rule in differential notation. I could write them in function notation also. The derivative of f of x times g of x would be g times f prime plus f times g prime, and the derivative of f of x over g of x would be g f prime minus f g prime over g squared. There's one other sort of whimsical way you might see the quotient rule written, just for fun, for memorizing it. People like to think of it this way sometimes, and if you enjoy that, you can go ahead and use that as your method of memorizing the quotient rule. Let's try out the quotient rule. For example, suppose I needed the derivative of x to the 8th over x to the 5th. Well, this is a silly problem. Of course, we know the answer is going to be 3x squared. But let's just practice the quotient rule. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. I haven't actually used the quotient rule or taken any derivatives yet. I've simply stated the quotient rule. Now, in my next step, I'll actually compute those derivatives. So x to the 5th times the derivative of x to the 8th, which is 8x to the 7th, minus x to the 8th times the derivative of x to the 5th, which is 5x to the 4th, all divided by x to the 10th. Now, if I multiply out those values of x to the 5th times x to the 7 and x to the 8th times x to the 4th, I get x to the 12th in both cases. Then when I collect like terms in the numerator, I have 3x to the 12th over x to the 10th, which is 3x squared. So it worked. We have verified that the quotient rule works. Now, if you're going to add the quotient rule to your arsenal of tricks for finding derivatives, I want you to be careful to not use it in cases where it gives you more work than you need to do. I'm going to enumerate 3 cases where I've seen people use the quotient rule when they don't need to. And the first case is the problem we just looked at. The derivative of x to the 8th over x to the 5th. We did all of this work to compute the derivative and saw that it was 3x squared, but really all you needed to do was recognize that the original expression should have been simplified before the differentiation, and the answer was 3x squared. Don't use the quotient rule in cases like that. The next case would be things like 5 over x plus x to the 7. If you're using the quotient rule where the numerator is a constant, then the first term is going to have this factor of 0 in it. The derivative of the numerator is going to be 0, and you're really just left with the second term. Instead of doing that, you can think of it as the reciprocal rule multiplied by 5. It's the derivative of the reciprocal of x plus x to the 7. So all you need to do is take negative the derivative of x plus x to the 7 divided by x plus x to the 7 squared. The reciprocal rule gives it to you in one step, and you can see that it gives you an equivalent answer. So don't bother using the quotient rule when the numerator is a constant. And the third example is don't bother using the quotient rule when the denominator is constant. In this case, the second term of the quotient rule has this factor of 0 in it. And instead of doing that, you could have just used the constant multiplier rule. The derivative of 1/5 of x plus x to the 7th is 1/5 of 1 plus 7x to the 6th. All right, but here, for the purposes of giving you practice, is a good example. Here's a problem that you really benefit from having the quotient rule. If you had to differentiate 3x squared plus 7x plus 3 divided by 2x squared plus 5x plus 2, what is the answer? Well, I actually gave you the answer It was right down here a couple seconds ago, but then I erased it. So hopefully you didn't see it. Try working through this problem on your own on a piece of paper, and then go back in the video and see if you could pause it and check your work with the answer that I gave you there.